everyone. Happy Monday. We're going to go ahead and start off today by reviewing the Bakeoff results from last week. So just as a refresher, last week's Bakeoff was on the task of sentiment analysis. So it was the 3-class task, positive, neutral, and negative. We were evaluating on the Stanford Sentiment Tree Bank test set that had a total of 2,200 sentences, and we used the macro F1 score as the evaluation metric. Basically like taking the accuracy on every class and then averaging all of those. So we had a pretty imbalanced test set with like 900 of the positive and negative examples and then 400 neutral. And in general, the worst performance was seen on the neutral class, which is kind of expected given this class imbalance. So here is a histogram of the scores that you guys submitted. The highest score was almost like 0.7. And the mode was around 0.5, 0.55. You can kind of see like where you fall in comparison to our like just basic unigrams plus softmax baseline, which is actually kind of like above this peak here. So that was pretty interesting that basic unigrams can get you so far. And so we have the winners of the Bakeoff. Before that. What's going to distinguish the high scorers from the low scorers. So we kind of looked at the like tokens that appeared in the submissions for the top scores, which we kind of defined as like scores that are above 0.58. And as you can see, it's like mostly kind of a lot of deep learning approaches, people who leverage BERT representations. And then in the low scores, it's kind of a mixed bag. You see some of the like baseline feature functions that were in the assignment originally, as well as like some glove tokens. So it's interesting to see like how far BERT has surpassed, approaches that are not even really outdated, but things that we were using just last year that were like winning the Bakeoff are now, in this low score section. So that's really interesting. Now on to our first place group. So congratulations to group 13, achieving a score of 0.692 using their balanced data set and end-to-end BERT approach. Group 13 used some smart data pre-processing. First, balancing the data set by oversampling, which was very smart because of the data set imbalance that I mentioned before. And then actually rejoining the contractions in the data set. And this is kind of like an artifact of how BERT was trained. So it's interesting that undoing the pre-processing essentially actually helped a little bit in terms of performance. And then they trained the BERT model end-to-end, basically fine-tuning BERT for the sentiment classification task. Good job to that team. Now for our second place team, group 51, used a similar approach of using BERT to create the feature representations and then using a neural net classifier on top of that. So congratulations to group 51 as well. They achieved a score of 0.651, doing a similar thing of fine-tuning BERT on the SST, and then running inference to generate the features for each sentence, and then feeding that into our torch shallow neural classifier. And they also used the strategy of kind of upsampling examples from the neutral class to do better on that class. And we also wanted to point out some other interesting approaches in addition to our top two teams. So we wanted to shout out group 9, which did super well, actually getting our the same score as our top team, but unfortunately can't qualify to win the Bakeoff because they actually use the subtree labels. But it's still a very interesting approach, so we wanted to point it out. This group actually formulated the task as a sequence-to-sequence task, using the strings containing the sentence annotations and tree structure as the input sequence, and then the sentiment label as an output sequence of length 1. So that was pretty cool. Basically the only group to think of formulating the problem that way. And actually one of the only groups among the top teams to not use BERT or Elmo. And then just using a 2-layer bidirectional LSTM for classification. And then we also wanted to shout out anyone who tried feature engineering. Unfortunately, feature engineering didn't make it into any of the top scoring systems, but that was interesting to us on the teaching team because last year's top 2 systems actually both used hand-built, bag of words based features with a simple logistic regression classifier. Although this year, a lot of the top teams relied on deep learning. This kind of shows a shift in the field. Yeah, so these are the top 2 teams from last year, and these scores aren't comparable to this year because they were for the binary task while we were doing the ternary task this year. But yeah, our teaching team is well represented here. But in first place, last year, Jada's team used pre-processing with just removing punctuation, and then character n-gram features of various lengths, as well as TF-IDF, and then just logistic regression classifier, and that managed to get a really, really good score on this task. So yeah, it's interesting to see how what we were doing last year with manual feature engineering has kind of been totally replaced this year by massive compute created pre-trained BERT representation. And second place, Lucy's team, shout out to Lucy, also used similar kind of feature engineering approach with very, very rich features, unigrams, bigrams, negation words, leveraging a sentiment lexicon. Yeah, so that's also a direction that you could definitely go if you were to you do the sentiment task, maybe in your class project or something like that. Yeah, and I think that's about it. Does anyone have any questions about last week's Bakeoff?
I wonder if there are representatives from the top 2 teams here. I wonder whether those are kind of theoretically the same system. Because it sounds like the first team used BERT and used a PITorch layer on top to fit a classifier, maybe a deep one. And the second place team just used our classifier as opposed to the one that the BERT team released. So I wonder if it's just a difference of how they were optimized, or actually maybe there's a deeper difference that I'm overlooking, but they look very similar.
Yeah, anyone from group 13 or 51 want to weigh in?
Because it must be that team 1 just didn't use torch shell or neural classifier, but rather something that's part of the BERT PITorch code release.
Yeah, I believe this group just kind of tweaked the final layers of the BERT model, the pre-existing PITorch implementation. Yeah.
This is cool too. This is common to see on deep learning code on the internet. You find that in some file somewhere in the code base, someone has done some very careful pre-processing. Presumably this is to sort of get properly into the BERT vocabulary or something.
Yeah, I was curious about this. They actually say on the BERT page, you should unprocess your token so it looks more like raw text.
Well, thank you. Yeah, and I've got my slides and everything. Maybe this will be my new solution. So thank you. Bakeoff stuff. First, I just wanted to say that Amazon gave us enough codes so that we can give $50 codes for AWS to people who win the Bakeoff. So the first team got their codes, and that winning team there will get codes, and we'll keep that up. It has to be just the top scoring system numerically because we don't have that many extras. Some more teams might get extra credit than that, but it is nice that we can reward the very top teams. Other Bakeoff stuff. So I posted Bakeoff 3 on Piazza. I think it's straightforward. It looks a lot like the procedure for Bakeoff 1 in the sense that you need to download some data, and then you're pretty much just running code that you've written. But of course, post on Piazza if there are any issues there. I also wanted to mention that there was a PITorch and NumPy tutorial on Friday, and the team produced great notebooks for that. I think it's especially. And so I posted those at the homepage at the top on the first day. It's a bit revisionist, but it's kind of like Introduction to Jupyter Notebooks, and now you have the stuff for NumPy and PyTorch. And I think the timing of that is really nice because you guys might be thinking about projects you want to do, and for your projects, you might want to dive into the PyTorch a little bit. And then the final thing I want to do here, before I dive into NLI, is just kind of introduce Homework 4 and the Bakeoff. And the reason I want to do that first is it's a kind of reversal. We're going to talk about natural language inference all week this week. And the Bakeoff is about natural language inference, but because the really good NLI datasets are enormous, I didn't want you to have to do that for a Bakeoff because it would consume a lot of time and a lot of resources. So instead, for Homework 4 and Bakeoff 4, we're going to do just a word-level entailment task. And this is kind of nice because it's like a microcosm of the whole NLI problem. It just removes a lot of the overhead from processing large data sets. And it's kind of nicely constrained in some interesting ways. So let me just start by introducing it because there are kind of 2 or 3 intellectual things that I think are worth calling out. So the framing. Throughout this problem set, the training instances are going to be pairs like hippo and mammal, just words. People have actually developed labeled data sets that just tell you for these at the word level whether the first entails the second. That's basically the task. So it's a binary task with vocabulary like this. Basically, because it's constrained to just words, you have to make just a few decisions here. So first, kind of like in Bakeoff 1, you need to decide how you're going to represent the pair of those words. So hippo and mammal are just items in your vocabulary, but you can look them up in some embedding space, first of all, and you can decide what embedding space, and it can be any embedding space. I guess the smart move based on past Bakeoffs is to use something like BERT or Elmo. Sorry, my phone is hardwired to stop, to shut off very quickly. I'll try to avoid that. So you'll want to look up hippo and mammal in an embedding space. You can also decide how you're going to represent them, right? So I think like what I've suggested here is concatenation, but you could do something else if you wanted. Difference or multiplication or sum, whatever you wanted to do. So embedding and then representation. And then from there, you're going to want to fit some kind of model, right? So the simplest thing would be to fit like a basic classifier. But you could have also a very deep network in there, right? Lots of hidden representations. And I'm going to leave it entirely up to you what you want to do there. I've fit a baseline that's kind of a shallow deep learning model, but you can do really whatever you want. And that's the Bakeoff. That make sense? And you can see that this is a microcosm of the whole NLI problem because after all, for NLI, it's just that hippo and mammal could both be complete sentences or very complicated noun phrases. But and also we have 3 labels, as you'll see, for our output space. But fundamentally, this is the same kind of problem. It just means that you can iterate much more quickly because the data sets are smaller and there's less to process. There's one other subtlety that I want to point out here. So you have a data set that comes with a notebook. It's already in your data folder. And there are 2 conditions for it. I've called the first one edge disjoint. And that just means that the pairs on training and testing, here train and dev, but also test, which I'll release as part of the Bakeoff, at the edge level, things are disjoint. What that means is that you could see a lot of the same vocabulary at train and test time, right? So like hippo and mammal, if you saw them in training, you won't see exactly that pair, but you might have seen hippo paired with other words and mammal paired with other words. And that's a kind of standard formulation of this problem, but it's kind of easy to game in the sense that the systems that result from this often look very good in terms of performance, but you might doubt whether they have actually learned to generalize because it could be that they've just kind of learned to triangulate within the space that they're in to do pretty well on the test set. And you can kind of see that because some baselines, which I'm going to tell you about later, tend to be very high for this problem. Like if I give you only the second word, what we'll call only the hypothesis, maybe you get like 80%. So we're not going to focus on that task. Instead, we're going to focus on this condition that I've called word disjoint. And what that means is that for train and dev, and also for test, the vocabularies are disjoint. So that means if you saw hippo and mammal in training, you will not see either of those words at test time. And it entails, therefore, that you won't see that, you haven't seen those edges before, right? So this is a strictly harder problem that is really testing your network's ability not only to do well at words it's seen, but also to generalize from that into other parts of the lexicon. Yeah?
I think you mentioned slightly above that one of the possibilities for the embedding is just a random embedding. Does that work with word disjoint if you had a random embedding?
It certainly does not. Yes, your intuition is exactly right. If you have a random initial embedding, then you will produce random results on the, not on the edge disjoint. You could do really well on edge disjoint, but on word disjoint, you will flounder. And what that means is that you need to initialize with a rich space. And you'll see in the baselines that I've put down here that I did glove. But kind of the striking and interesting thing about this is that initializing with glove, or I assume with BERT and Elmo, really gives you a lot of traction on this problem, even on the word disjoint condition. So I've walked through just to show you in a bit more detail in this notebook what these two data sets are like, and I've kind of built up this argument here for why we might want to use the word disjoint condition. I also set a baseline which uses these glove vectors here. So that as the kind of fundamental representation of the words, you just do a glove lookup in a way that you guys have done on earlier problems. And for my baseline combination function for the two words, I just use concatenation. And then for the classifier, as I said before, I use this torch shallow neural classifier from the course repo. 50-dimensional hidden representations, a modest number of iterations. And as you guys are probably accustomed to at this point, we have this kind of little experiment wrapper that should make it pretty easy for you to run experiments. So, you know, model is your the model that you want to test. It could be anything. Glove vec and vec concatenate. Those are really the 3 points that you'll want variation on. And you'll probably just want to use train and dev there for your development phase. So for my baseline, I got macro average 0.69. Which is pretty good. But obviously the goal for you in doing the homework and the bake-off is to see how much you can build off of that baseline with a richer network or more interesting representations or more and different ways to combine the two word vectors to form your input representation. Is that making sense so far? Any questions, comments, concerns? It should be a fun one because you can really develop models fast, so you should be able to try a lot of different things. This is sort of anticipating stuff that I want to discuss for you, but let me just walk through the rationale for the homework. So the first one is called hypothesis-only baseline. As you'll see as we go through the material, people discovered a few years ago that you could actually do really well on many NLI data sets if you threw out the first part. So in my hippo-mammal pair, just throw out hippo and make your classification purely on the basis of the word mammal. And I want to discuss that with you because I think it's kind of an interesting thing that mixes maybe some artifacts in these data sets, but also a pretty deep fact about how the lexicon is organized and what it means to be in an entailment relationship. I mean, if you think about that, it's not surprising that mammal would be more likely to occur on the right in an entailment pair than the left because of its generality. Oh, and actually, this fact about hypothesis-only baselines was discovered by a student in this class, which I think is really cool. As far as I know, the first person to observe this for the SNLI data set, which is a big entailment data set, was a project in this course in 2015. And then subsequently, a number of other groups discovered it and quantified it. So what we're asking you to do here is to just see how strong the hypothesis-only baseline is for this data set. And what we're trying to signal there is that given this prior work, if you tackle an NLI problem, then basically you should fit a hypothesis-only baseline because random is not your baseline at all. It's actually this one. So it asks you to do that. That's pretty straightforward. And then it just asks you, in the spirit of thinking freely about this, to explore an alternative representation to concatenation so that you might think about some interesting kind of a priori ways that you might combine the two representations. Maybe difference is interesting for an entailment space, or multiplication, or something like that. And then this is where that PITorch tutorial might come in. I'm going to ask you to do a little bit of work kind of subclassing one of our PITorch classes and adding essentially another layer and a dropout layer.
Dropout is a form of regularization that's very easy to implement in PITorch. I've kind of presented the mathematical details here, but I think you'll find that the important thing is to just use the PITorch documentation to figure out how to add into your sequential model a dropout layer, and then you'll be off and running. And again, the spirit of this is to get you thinking about how regularization for your networks might be a powerful technique to avoid overfitting and stuff like that. And I've kind of started you and given you some instructions, and we're happy to talk with you about the best strategy for this kind of coding on Piazza. And then finally, as usual, you do your original system. We'll see what happens. I don't think I have to impose any rules on this. You can download vectors from the internet. You can download code as long as you do something original with it. And the reason I can say that is because the Bakeoff will be conducted on a held out data set that I have not given you. So you can do all the development you want on the data we've provided. Just don't overfit too much, because then you'll get hit at test time in the Bakeoff. Make sense? Any questions about that before we dive into the regular material? So that was a small glimpse of the problem that you'll be exploring. But what we're going to focus on this week is the problem in its fullness, this problem of natural language inference. I think this is a wonderful problem, because I think it gets at something really deep about what we're trying to do in NLU. And also there is an abundance of really interesting data sets at this point, because the field has kind of triangulated on an interesting methodology for collecting these data sets. And people have found that it's pretty easy to crowdsource good ones. I mean, there are some issues that we'll discuss, but by and large, this has kind of been productionized. And so you have multiple data sets that are in the same format, making it very easy to experiment. So I don't encourage having a default project for this course, because I think it's interesting for you guys to get creative. But if there were a default project, I would certainly say it should be something with NLI, because it tests lots of the concepts that we've introduced. There's a really wide space of models that you can explore, and these data sets are so good. I also want to say that there are many special connections to this course for NLI. So it used to be called RTE until Bill came along. For his thesis, he started calling it natural language inference. And Bill did lots of seminal work in this space, kind of exploring how you might apply natural logic, which has a very rich algebra of inferential relationships, to NLP tasks in this space. And so Bill is part of the resurgence of interest in this problem. And then Sam Bowman was a student in this course. Sam was also my student. And I think the full history of this is that Richard Socher came and gave a lecture on tree structured networks for sentiment analysis. It was about the time that we were developing the Stanford Sentiment Tree Bank, and Sam was captivated. I think Sam was not focused on NLU at the time for his research, but that was a kind of important moment for him. And he wanted to work on NLI because I think he admired Bill's work, and he liked thinking like a semanticist. But there weren't really good data sets. He felt kind of stuck by the ones that were available. And he just did the really admirable and ambitious thing of saying, let's collect a massive data set for NLI so that we can test these new deep learning models. Because one sticking point at that point was that the available data sets were kind of too small to really test these deep learning approaches. So Sam developed SNLI, and the rest is history. The task has been renamed. Nobody says RTE anymore. And we have all these interesting data sets. And Sam has been a real powerhouse in terms of developing new ones. So he's responsible for both SNLI and multi-NLI, which is the two data sets that we're going to concentrate on. And then just while I'm in this vein, I want to mention also that both are both working hard on NLI problems right now, kind of using it to stress test neural systems to see what they're actually learning about semantics, using them as a test bed for interesting new neural models that he's developing with some researchers at IBM. So there are lots of us on the teaching team who are interested in talking with you about NLI. Here's my overview. I'm going to give you a bit of background on the problem, and I'm going to introduce these two data sets, SNLI and multi-NLI. And then we're going to do the kind of standard narrative for this course. I'm going to show you some hand-built feature functions, which I think are really good and interesting baselines for the problem. And having done that, then I'm going to show you that we have in the course repo a nice framework for doing experiments on all these kind of SNLI style data sets. From there, we're going to start to look at deep learning models. And NLI is interesting as compared to sentiment because basically you have two texts to work with, the premise and the hypothesis. And that opens up lots of interesting avenues for doing modeling because you can think about how to model the premise and hypothesis separately and how to relate them, and then finally how to fit a classifier. So we'll look at sentence encoding models, chained models. Those are kind of the main classes. And then as an orthogonal development, I'm going to show you some stuff on attention, which has really risen to prominence recently. I think NLI and also machine translation were kind of motivating problems for attention in NLU. So we'll talk about those kind of things and how you might add them to your systems to do even better. And then finally, we'll talk about error analysis. These things will probably come on Wednesday. We'll see how things go. But I think, again, because of NLI's very rich grounding in linguistics, you have some very interesting avenues for thinking about error analysis and how it might relate to linguistic patterns and logical patterns and stuff like that. So that's our full plot. As usual, we have a lot of material. So nli.py is your main module, both for the homework and if you want to work with these larger data sets. And then there are two notebooks. So the task and data one introduces SNLI and multi-NLI and shows you the code that we have for working with them. And then the second notebook is a whole lot of modeling code to kind of get you started if you want to pursue this task. We've gone over homework 4 and Bakeoff 4. And then I'll just mention that the core readings in my mind, we posted a few more, but I would say the core readings are Bowman et al. 2015 that introduced SNLI and set up some initial baselines. And then this Ruck-Taschel et al., that's a seminal paper in terms of introducing attention, word-by-word attention, into the NLI problem and showing that it could lead to big gains. And then I also recommend some auxiliary readings. So the Goldberg 2015 is that primer on deep learning models that I also recommended in the last unit. So that's kind of separate. Then for NLI in particular, Dagen et al. Is a very important foundational paper that more or less introduced the task of RTE. And then MacCartney and Manning, that's a nice presentation of this natural logic approach that Bill developed. And then Williams et al. Is the paper that introduced multi-NLI. And that's another good resource for you in terms of baselines and in terms of understanding what's in that data set. These are typical NLI examples. I picked them a little bit strategically just to give you a sense for the kind of variation that we see. So the top one there, you would say that turtle and linguist contradict each other. That would be the label for that pair. In our homework, we just have yes, no, and entailment, but in the data sets that we'll focus on today and on Wednesday, you have three-way labels: contradiction, entailment, and neutral. And so we would say that turtle and linguist contradict each other. There's already some complexity there because you can easily imagine a possible world in which some turtles are qualified as linguists, right? You can kind of already see that we're not going to be dealing with a notion of logical contradiction, but rather something closer to common sense inference based on world knowledge. A turtle danced and a turtle moved, that actually might be closer to just being a true entailment fact because of the lexical relationship between dance and move. The only assumption you need to bring in there is that these two turtles are the same turtle. And that's actually a touchy point when you get to naturalistic data, and I'm going to return to it. But kind of what we're doing now is making some assumptions about event or entity co-reference across the premise and hypothesis. And in that case, dance entails move, and so we get entailment. Yeah?
Yeah, since you're doing a common sense here, I guess, so you're assuming that turtles can dance. I guess the question is, where do you get, this base of, common sense knowledge?
Oh, that's interesting. I guess to be careful about it, I'm not assuming that a turtle danced, but rather if a turtle danced, then a turtle moved. I think the flavor is much more like that. But again, with some qualifications, because this is naturalistic data, as you can see, it's actually based on image captions, and so there is some commitment to the premises being realistic. I guess I just like turtles, and that's why I picked it.
So in the first example, it's more like a turtle can be a linguist kind of thing, right? It's because you're interpreting that within the real world. Does that make sense? I'm
yeah,
I guess
fair.
it's hard for me to see the difference between the two.
Because you can imagine a world in which a turtle is a linguist?
Yeah.
Yeah, fair enough then. You would be probably the outlier annotator if you were asked to do the annotation, but you have a defensible point. The logician in me wants to say, that's certainly not a contradiction, the first one. And that the second one is not necessarily an entailment unless I have proper existential closure of the two variables across the premise and hypothesis. Yeah, this is the kind of thing you have to get used to.
How do you check for like common sense knowledge, like for the first example?
I would frame it differently. I would say it's not so much checking for common sense knowledge as acknowledging that this is pervasive in this task. And that the way you might even think about the NLI problem is as one that requires an understanding of common sense reasoning and kind of world knowledge, and that's fueling the system doing well at these problems. But it's really difficult.
So I kind of also sided on the turtle linguist when I felt like it was more neutral to me. But why do
I love it. Yes. You live in a magical world.
For the turtle dance and the turtle moved, I was a little curious why you're saying it has to be the same turtle. Isn't it because it's a turtle dance, then that implies that at least some turtle has moved, and so a turtle doesn't have to be the same one?
Well, that's a fair point actually for this one. Yeah, it would just follow logically that if any old turtle danced, then there is some turtle that moved. Yeah, that's fair. Yeah. Every reptile danced, a turtle ate. Those would be neutral. Again, that's sort of a logical fact, I think. Some turtles walk, no turtles move. Those contradict each other. And this is a classic example from Bill's thesis. James Byron Dean refused to move without blue jeans, entails James Dean didn't dance without pants. I guess Bill is highlighting not only the kind of linguistic complexity of this reasoning task, because it might take you a minute to see that those are in an entailment relationship, but also that as part of this, you might have to solve some stuff like figuring out that James Byron Dean and James Dean are the same person. And for that, you might need a lot of world knowledge of a particular kind. But I think that those follow more or less logically. We don't need much common sense reasoning there. That will be very different for the next one. Mitsubishi Motor Corp's new vehicle sales in the US fell 46% in June, and Mitsubishi's sales rose 46%. Oh no, that one's straightforward. That's just a contradiction. Fall and rise. I guess we have to make some assumptions about the domain of these claims, and I'll return to that. But by and large, those seem like they contradict each other. This next one definitely involves common sense reasoning. Acme Corporation reported that its CEO resigned, and Tails, Acme's CEO, resigned. It certainly doesn't, because companies can report anything they want, and sometimes they report false things. And so strictly speaking, if we were semanticists, we would say that this report has no entailments with respect to the complement there, Acme CEO resigned. But again, it's a kind of common sense thing. Given that we know that this corporation is likely a reliable source about this kind of information, then we might infer entailment, or annotators might be encouraged to infer entailment.
It's not the James Byron Dean and James Dean one. In my mind, I feel like we're walking a fine line here because to assume they're the same person, because take the example of like George W. Bush and George H.W. Bush or something. If you called one George Bush and the other, you had to specify by quantifying their middle name or something.
That's a great point. Yeah. Maybe in the back of your mind, you should be thinking that there's a practical side of this, which is that we want systems that could just read through newspaper text, for example, and figure out what the entailments are or what the logical relationships are. And in that case, this isn't a problem we can ignore. Rather, we need systems that are sensitive to that level of distinction and that know how many George Bushes there are at some implicit level, and that can also resolve these to the same entity. But the uncertainty that you guys are feeling, this is wonderful. You sound like linguists. This is the linguist reaction to this problem is usually none of these things have any of these logical relationships. It's all neutral because I can think of edge cases where it falls apart. And I have to just retreat to the idea that we're kind of trying to get a hold of what you as a reader would infer from these texts or infer from these pairs of sentences.
So just a follow-up on that as well. Is there a way to rephrase the task so that it can detect the ambiguity or sort of report it or relabel it? And if so, how would you go about doing it?
Sort of make finer distinctions between logical entailment and common sense reasoning and abduction and all these other notions that are in play here. I think, yeah, here. So this kind of summarizes this, and I would refer you to this trio of articles. This is a kind of back and forth. These are all Stanford people, or at one time they were all Stanford people, kind of having a debate about how much non-logical reasoning we should allow to creep into this problem. And so I think I won't resolve it, but it's an interesting discussion. I do think, though, that the top of this kind of summarizes the view that I'm trying to convey, which is, does the premise justify an inference to the hypothesis given some common sense assumptions about the world and the speaker and our intentions and so forth? Yeah, that's the heart of it. And then the other aspects of this problem is that there's been a focus on kind of local inference, so just premise and hypothesis. And there's a lot of emphasis on capturing variability in these expressions, like different ways that you might refer to people, different ways that the same concept might be articulated, and so forth and so on. I do think that what happens if you try to be strict about this and say that you're going to look only at logical entailment is that the problem gets kind of small and limited. It's basically just like really reliable lexical relationships. And then even then the linguists come in and say, wait a second, word sense ambiguities are causing me even to doubt this thing that you thought was a solid entailment. Then it all kind of falls apart. And that's the story I tell myself about why it actually makes sense to think about this as a common sense reasoning task, as much as I might like logical inference. This is kind of nice. This is from that important paper by Ido Dagen and colleagues that introduced RTE, what we now call NLI. And I'll just read this. It seems that major inferences, as needed by multiple applications, can indeed be cast in terms of textual entailment. Consequently, we hypothesize that textual entailment recognition is a suitable generic task for evaluating and comparing applied semantic inference models. Eventually, such efforts can promote the development of entailment recognition engines, which may provide useful generic modules across applications. I think that's a nice articulation of a dream for NLI as a task. The idea would be, if we can get our systems to be really good at this kind of basic but pervasive logical reasoning, then the capabilities they have would apply in lots of domains. And that certainly resonates with me as a semanticist, because I kind of think of entailment and contradiction as being really central to how we think about language, how we reason with it, how we use it, and so forth. Yeah?
Could be used to, like, for example, say someone made a query, but they like sort of misunderstand what they're like trying to get at, but it entails like the same like generic thing, so you like go to the other thing that entails the same thing. Does that even make sense? Sorry.
I mean, you're speaking Ido Dagen's language, right? You're keying into his framing, which is to say, like, challenging problems in NLI, maybe they turn on misunderstanding or reformulation. We can actually reduce them into an NLI task, and that'd be wonderful, because if we could, then the models I'm showing you today would have a lot more applicability. So I'm not sure precisely what you mean, but I'm really open-minded about this. And I've actually tried to do some of this here. This is actually taken from Ido Dagen's article. Paraphrase detection is a well-known task. You could think of that as just the task of saying, is the text and its purported paraphrase equal in some extended sense of common sense reasoning? Or summarization would say, does the input text entail the summary, which would be like saying we want, at least as a constraint on summarization, that the result is somewhat more general than the input. Information retrieval could go in the reverse direction. You could formulate that as saying that you would like essentially to return documents that entail the query in the extended sense of NLI. And then question answering is one that you can basically reduce to saying that you want the answer to entail the question if you are willing to massage the question into a declarative form a little bit. So for example, if you were willing to replace in English all the WH words with indefinites so that who left became someone left, then you have a straightforward NLI task, and you're really saying you would like an answer like Sandy left to entail someone left. And you would call that your notion of answerhood. And I think there are other tasks out there that you could try to reduce to the same form. And that's the inspiring idea, that we've really gone kind of down to the metal here in terms of understanding reasoning in language, which is applicable to lots of different areas. Again, by way of background, this is sort of interesting. This is a landscape of different approaches that people have taken to the NLI problem. So up here I have logic and theorem proving. Those are kind of the earliest approaches inspired by logic and linguistics. And I've put them very high on the depth of representations axis, because of course they give you very high fidelity pictures of the data. But along the x-axis, I have effectiveness, which is kind of like, if you give me a whole lot of data, does this model do good and interesting things with it in a comprehensive way? And the main limitation of logic and theorem-proving systems is because they tend to be handcrafted, they're high on the y-axis but low on the x-axis. Bill developed this natural logic approach, which was kind of intermediate. So it was very rich logically, but because the logic is defined over natural language utterances, you have a lot of power to apply it to larger data sets. And so it kind of moved us to the right along the x-axis, with some sacrifice in terms of the depth of representations, but still very rich. Below that, I put semantic graphs, which was another kind of handcrafted approach that depended a lot on very high fidelity alignments between the premise and hypothesis. Again, getting more effective with some sacrifices in terms of interpretability and so forth. And then over here at the top, I have clever hand-built features, kind of as exemplified in this production system called the Excitement Open Platform, which is a good kind of classical system for solving the NLI problem. And then down just below it, I put n-gram variations. We're going to look at some of those today. So by that point, you're very effective. Those models can be very powerful, but very low in terms of them offering a deep understanding of the NLI problem. Basically, you just have a lot of superficial associations. And then something interesting has happened. So I put Deep Learning 2015 there, because in 2015, when we really introduced this task into the course proper, the deep learning models were not really a slam dunk. This was kind of before or just at the time SNLI was being introduced. And by and large, those systems were being beaten by handcrafted ones. I do think it's safe to say that by now in 2019, deep learning models have overtaken the hand-built ones, to the point where even for the little experiments that you see in my notebooks and so forth, it's very easy for you to beat a very strong handcrafted features baseline using some deep learning techniques. And then I mentioned that there are a lot of data sets. Here's a whole bunch of them. So the Fracas textual inference test suite is interesting historically because that is an attempt to have a data set where basically you have been confined, at least for the parts that we're talking about, to logical inference problems. So it's small, but I think still really interesting as a kind of test set if you want to distress test your system, for example. And then pre-SNLI, there were a few data sets like SemEval 2013, SemEval 2014. That was the SICK data set, which I actually distributed as part of the data set for the course because Sam Bowman put it into the SNLI format. So it's there if you want to play around with it. But again, it's kind of small and had some idiosyncrasies. And that was before SNLI. And then after SNLI, you have a flourishing of data sets that are in the same mold. So MedNLI is for medical stuff. Very challenging problem, very rich vocabulary. XNLI is multilingual NLI datasets that have been derived from multi-NLI by a group at Facebook. Diverse natural language inference collection is, again, a really large-scale, very diverse set of problems from a group at Hopkins. SciTail is SNLI-like, but it's derived from science questions and multiple choice questions and also web text. So that's also really challenging. And then I put two just to kind of get you thinking about this in the mode of Ito Dagan. So like the factoid question answer corpus can be thought of as a kind of NLI problem if you want to put it into that mold. Or the pen paraphrase database is just a simple version of NLI where you're trying to get just one relationship. And then really interesting, this is a newer development. The GLUE benchmark was released by Sam Bowman and his group. And what they did is, it's a whole bunch of NLI tasks, I think 5 of them. And then a whole bunch of other tasks that aren't strictly NLI problems, but are meant to kind of test the Dagan assumption that if you have a good NLI system, then those representations will transfer to other tasks. And a lot of people have been working with that. There's a lot of progress right now on the GLUE benchmark. So for a very ambitious final project, you could tackle that in whole or in part. I think I'll skip over this. These are some different label sets that have been explored over the years. For better or worse, we've kind of consolidated on this 3-way one because of SNLI. But before that, there were 4-way versions and simpler 2-way versions like you'll explore in the homework. I mentioned this before because this is relevant for the homework. I have you testing this hypothesis. Yeah, so Landon Kesselman in this course for his final project observed the strength of hypothesis-only baselines. And it's been substantiated by a bunch of other groups, including one by Sam Bowman. It's interesting to ask why this holds. So why could you get any traction at all if you were just shown the hypothesis in a premise-hypothesis pair? Initially, that sounds very worrying, right? Because it sounds like there's something deeply problematic about the data that would allow you to leave off so much of your example and still do well. I think it is something to worry about, but I'm not myself so worried because I think this has a principled explanation that is more or less grounded in the problem itself. And I've kind of summarized that in these 3 statements here. So specific claims are likely to be premises in entailment cases. That's really easy for me to imagine if I think of the WordNet hierarchy. So WordNet is basically a huge hierarchy of entailment relations for nouns. The things that are at the bottom of that hierarchy are very specific things like puppy and kitten. And they entail almost everything else in the hierarchy on up to object. So if you show me just the word puppy or kitten, I have a very good guess about whether it's in the premise or the hypothesis. Conversely, if you show me something very general like mammal or object or dog, then it's very likely to be on the right in that pair just because if I drew another word from the vocabulary, it's unlikely to be above it because so few words are. And then this extends also to contradiction. So I think that specific things are more likely to lead to contradiction by the kind of rules of the SNLI game because we make some assumptions about event co-reference and so forth. And if you've described something very specific in these terms, it probably excludes most other claims. And so again, very specific things likely to lead you to contradiction on either side. So I think it's the result of these 3 observations that is driving a lot of the strength of hypothesis-only baselines. And if you believe that argument, it means that this isn't really something we're going to be able to naturally factor out because this fact about the entailment hierarchy is something that we want our systems to learn. It's an important semantic fact. And if you decided, for example, that you would get rid of it by balancing your data set so that every word had equal likelihood of appearing as a premise or hypothesis, you could weaken the hypothesis-only baseline, but it's not so clear to me that the resulting systems would be solving the problem as we encounter it in the world. And for that reason, my response to this is just to say, let's always have in the top of our results table a hypothesis-only baseline so that we know the starting point for our task. Does that make sense? Anyone want to push back on that? Yeah.
Does a premise-only baseline do anything?
It's underexplored. If you believe my generalizations, it ought to be better than random because I think there is information in just that part, but I haven't explored it too much. My code should make it really easy to explore. Okay, this is good timing. Let's dive into what these data sets are like. So we're going to look at SNLI and multi-NLI, which are a kind of common mold for data sets like this at this point. So here's a quick summary. It was released by Bowman et al. 2015. All of the premises are image captions from the Flickr 30K data set. And that's really important to keep in mind because image captions are kind of unusual bits of language. And it also means that all of these things, at some level, for people who produce them, were grounded in a specific image. And I think that has shaped the data. The hypotheses were all written by crowd workers. So this was a very large crowdsourcing task because this has over 500,000 examples, and all of those hypotheses were written by people. And then parts of the data set were evaluated by other humans. Right. I should note that some of the sentences reflect stereotypes. This is a nice paper from a Hopkins group again, just pointing out that, as you might expect, people who were doing lots of crowd work kind of relied on some shortcuts to producing contradiction and entailment pairs. And a byproduct of that is that they end up relying on problematic stereotypes. So this is something we would like to eliminate from these data sets because we don't want to perpetuate these problems. But for now, I can just say that you should be aware of this. Yeah, so about 550 training examples, 10K dev, and 10K test. I've given some information of like the mean length of the examples, the types of clauses. So they're not all sentences. Some of them are noun phrases. It's got a fairly large vocabulary, almost 40,000 words. And then it has a smaller subset of about 60,000 examples that were validated by 4 additional annotators, if you want increased confidence that the label is correct. And that went rather well. There was a very high level of agreement for the labels. And then finally down here, there's a leaderboard, which has a truly overwhelming number of papers on it now. It's kind of hard to digest, and I think we're past the day where you would just like hope that you were the highest row. I would think about it somewhat more flexibly. So Sam already divided it into a few different model classes, and you could think about where you want to slot in. And then another distinction that has emerged is just whether or not your model is an ensemble. I would say that for SNLI in particular, we've entered a phase where ensemble models are just doing best. And that's an interesting game if you want to just pursue raw performance, but it's a kind of different thing you're doing in the modeling sense than picking a single model that you think reflects an intuition about the data or the problem itself and pursuing it as far as you can. So think in a nuanced way about how you're doing with your system with respect to the leaderboard. This is a screenshot of the crowdsourcing methods that were used. It's kind of small. It's here just as documentation. Obviously, for crowd workers, we couldn't just tell them, hey, construct a sentence that entails the premise or contradicts the premise, because that's a kind of specialized logical notion. So I think we found a way of framing it so that it was pretty clear what we were after, but more naturalistic. But if you want to do a deep dive on what the data actually mean, this is important information, because this is the starting point for how the examples were constructed. And here are some actual examples. These are the ones that are given in the paper. A man inspects the uniform of a figure in some East Asian country. So remember, that was the caption of an image. And then the contradiction pair that the worker came up with was the man is sleeping. And in a subsequent validation phase, all 5 people agreed that that was a contradiction label. I think these are pretty straightforward. You can kind of see that it looks, anyway, like contradiction is very consistent. And there's more nuance, especially around what the neutral categories mean. I think that's borne out in the data. Here are cases that I picked, again, just to reintroduce this idea that it's not so obvious how we're defining this. So these aren't actual examples from the corpus, but I think they abide by the standards that were adopted. So here's the idea. A boat sank in the Pacific Ocean and a boat sank in the Atlantic Ocean would be labeled as contradiction. Of course, those 2 things could happen together. So there's no logical sense in which these are contradictory. But if we assume that what we're doing is talking about a single image, like from the image flicker 30K data set, then it's likely that these contradict each other, that only one of them could possibly be true. And that's the sense in which this is a contradiction relation. And here's a more extreme case that Sam came up with. So Ruth Bader Ginsburg was appointed to the Supreme Court, and I had a sandwich for lunch today. By this logic, you would say that those were contradictory. Again, not because they couldn't both be true. Maybe they are both true of you or of me, but rather that they couldn't be describing the same event in some sense. Does that make sense? This is tricky stuff. I mean, we're more or less at the mercy of the data that we have, but all this is worth keeping in mind. Okay, and then the other data set I wanted to introduce is multi-NLI, released by Williams et al. In 2018. It's very similar in terms of its design with some added nuance. So first, the training set is drawn from a bunch of different genres: fiction, government reports, the Slate website, the switchboard corpus, and some travel guides. And then for the dev set, you have one condition where you test on those same genres, and another where you test on some completely different genres. And those are the 9/11 report, Face-to-Face, which is some narratives, fundraising letters, nonfiction, and articles about linguistics. And that's a really cool idea because you might think that that's a way, again, of stress testing your system, of forcing it to go outside of its training experiences. Again, it's very large. It has the same kind of additional annotations for validation. And then the one twist here is that I think to avoid kind of a lot of hill climbing on the test set is released only as a Kaggle competition to kind of reduce the number of times that people can evaluate on it. And you can check out the project page. I think it links to a leaderboard and some other information.
Your slide for the data set, I was curious if the captions for the images have to be maximally informative. Say you have like a picture of a soccer game happening and then the premise is like a man kicks a ball and then the hypothesis is like a man is watching the game or something. So they're both happening in the same photo, but the photos of multiple events.
That's a great question. So basically, like, how comprehensive can we count on the captions being? I think you can't count on anything. I think image captions are strange things that reflect what humans regard as salient. And so they have their own interesting biases. And there have been some attempts, like here at Stanford with the Visual Genome Project, to do image captioning of a sort that's not so naturalistic to really comprehensively label what's in the images. But that's not what was done for Image Flicker 30K. It's much more naturalistic. And so you're starting in an interesting social and linguistic space and then building on top of it in an unusual direction. That's the long and short of it. I've always thought, though, that there's an opportunity here, which is that you might leverage the actual images. This has been done infrequently or not at all. But you can imagine that you solve the problem by reasoning not only about the premise, the image caption, but also about a representation of the image itself. Sorry about the phone doing that. Here's another really interesting thing about the multi-NLI data set. So Sam and the group, they released with the data set a bunch of annotations for properties of the individual examples. So, for example, they just labeled some as being active-passive pairs in the premise and hypothesis. And that's really interesting because you expect that to be kind of meaning-preserving. But it's an open question whether your system can be sensitive to that kind of transformation. Or also categories like whether there's a belief predicate, like believe or claim or say, whether there's conditionals, whether co-reference is crucial. Because many systems just ignore kind of like the pronouns, but entailment can often hinge on the nature of those co-referential relationships. Is it a long sentence? Does it contain modals and negation? Could these two things be called paraphrases? Are there quantifiers in the sentence? These are kind of quantifying the semantic difficulty of the examples. And this is really nice. You'll see this later when we do error analysis. You can use these categories for a kind of out-of-the-box error analysis. You can ask for a bunch of different systems, which of these categories are they doing well on and where are they failing? And that's often very illuminating. Okay, and just to round this out, just so you know about it, this is also in those notebooks. Here is some code for dealing with these data sets. You have basically SNLI train reader, SNLI dev reader, multi-NLI train reader, and then you have the two dev readers matched and mismatched. And so those should be good, like easy ways for you to interact with the data and feed it into machine learning systems. And I think the only thing you have to get used to is they yield what are called example objects. You can see that happening, I guess, here. And that's because the underlying data has not only the strings and the relationship, but also, if it was multiply annotated, all the decisions the annotators made, and also binary and non-binary parses of the examples, which are automatic parses that come from Stanford's Core NLP package. But they're good parses by and large. It worked well. And that gives you access to very rich tree structures if you want to make use of them. And so that's a bit of a glimpse of how you deal with those example objects. And here's another example. I know it's small, but it's there for you to download and check out if you like. And then here's a bit of additional code that just shows you the interface that we've provided for dealing with the annotated subsets so that there are no obstacles to you making use of it, because I think it's really exciting to stress test your system by looking at how it does on different classes of problem. And they've made that very easy for us. Excellent. Any questions about those data sets at any level before we start to dive into the modeling parts of this? We'll kind of embark on our familiar plot then. So the first thing that we'll do is look at some hand-built feature functions and some kind of classical linear models, and then we'll move into deep learning. What I've done here is define just two very simple baselines. Oh, that's nice. I made that bigger. That you see a lot in the literature. The first is what I've called word overlap phi, and it's just creating a feature for every word that occurs both in the premise and the hypothesis. So that gives you pretty sparse models, and they're pretty small because you're really looking at only the overlapping words. You can contrast that with word cross product, and what that does is create a feature for every pair of words that occurs in the premise and the hypothesis. So, the full cross product in the sense of you think about them as two sets of words, you look at every pair that you can draw from that pair of sets. And that leads to really enormous feature spaces. I think that if you fit a model with this feature function on all of SNLI, the training data, you end up with well over 1.5 million features. So very high dimensional, very sparse feature space. Yeah, here's a way of looking at that. So like if I have Toby is a dog and Toby is a big dog, then the word overlap thing just keeps track of Toby, dog, is, and it drops out big. Whereas the word cross product thing creates this enormous list of all the pairs that I can form from those two sets of words with their counts. So much, much bigger. Those are kind of baseline things. Here's something else, a whole class of features that you might think about that could come from WordNet. So as I said before, WordNet is a kind of very high fidelity, handcrafted resource full of information about word-level relationships, in particular entailment relationships and some contradiction information that is in the form of antonyms. And what I've done here is just give you a little bit of code that shows you how you might create feature functions relying on the WordNet hierarchy. So as a quick example, if I just look up puppy, I get all its synsets, and they're like dog, pup, and young person. So you can see that the sense of the word puppy is kind of ambiguous, and WordNet is capturing that. If you go for just the first of those synsets, then you get a kind of more conservative perspective, because the first sense, I think, is the most frequent, according to their data. And so from that, and actually there's lots of methods you could use, hypernym, hyponym, and so forth. Here's a little example of how to create a WordNet feature. And I've done it for hypernyms and hyponyms, and I'll just show you an example. So again, if I have the puppy moved and the dog danced, then hypernym features would give me a feature for puppy and dog, and hyponym features would give me moved and danced. And you could do, with this code here, you could do this for lots of other WordNet relationships, and I think carve out pretty interesting subspaces of like lexical entailment and contradiction and so forth. And here are some other ideas. So you could do lots more stuff with WordNet. You could also think about some edit distance features between the premise and hypothesis, maybe at the word level. I showed you word overlap, but maybe it's even more natural to think about word differences. Maybe much more of the story is told by what is in the hypothesis but not in the premise, or the reverse. Alignment-based features, that would key into an older idea from NLI that it's kind of important to figure out how the premise and hypothesis, relate to each other. Negation, of course. I think it's worthwhile having separate features that would key into negation, as well as other lexical classes, because all of this stuff is really deeply affecting entailment. Things like verbs of saying and attitudes and modals and hedges and all that stuff. A lot of stuff that I think is relevant for sentiment carries over here because of the way it modulates claims that we make. Quantifier relationships, of course, you'd want to capture those. They are not in WordNet, but definitely worth maybe even the effort of hand coding them. And then you could also have named entity features. That's kind of like the James Dean, Jimmy Dean, James Byron Dean situation. And this is not meant to be exhaustive, but rather just to get you thinking about different ways that you could key into lexical information, constructional information, and also world knowledge. All that stuff should be brought in given the way we framed the NLI problem. Questions about that? Or comments or ideas? All right, NLI experiment. Again, this is the pattern that's repeating for all of this code stuff. It's kind of standard language for thinking about running experiments in a productionized way. And I've provided a bunch of code for that. Let me just walk through it at a high level, just to show you how easy this could be. So as usual, you point your repository to the data. Here, that's SNLI home. Here, just to illustrate, I've defined word overlap phi as my feature function. As usual, we have these wrappers. Here it's fit softmax, so that you can, as part of the experiment pipeline, do cross-validation and fiddle with the parameters and do other things that are part of model setup. Slightly different from the Stanford Sentiment Tree Bank, we have these reader objects. So here I've set up train reader 10, and the reason for that is they have this extra argument called sample percentage, samp percentage. And here I've set it at 0.1. I think that's really important for development because if you leave that off or say samp percentage equals none, then your experiments are going to be run on the full 550K examples, and your progress will slow to a crawl because every experiment might take hours or days. So what I would encourage as at least one way that you would develop on this data set is to do it on small subsets, which are randomly selected. And then once you feel like your system has stabilized, expand out to a larger chunk of the problem. So you set up that train reader, and then it's going to look a lot like the SST, right? So you have the train reader argument, your feature function, word overlap phi, and fit softmax. It's like a Swiss Army knife. You have a lot of other options, but those can be left off. And that's pretty much all it takes to run an experiment. And as before, basic experiment there is a dictionary that more or less stores all the information about your experiment for reproducibility and error analysis and so forth. Does that make sense? That's the basic framework. Very familiar, I think. Let me show you two other things that I would encourage. So first, hyperparameter selection on trained subsets. So again, unlike SST, where it's small enough that you can kind of do a lot of experiments in a pretty manageable way, when you move to the level of SNLI, every experiment is a major investment. And again, you just won't make that much progress if you're not thinking about how to do smaller stuff that will inform the full picture. So I'm going to show you, or suggest to you, two ways that you might do that when it comes to hyperparameter selection. So first, let me just set this up. This will be on trained subsets. So you point your data, SNLI home as usual. Word overlap phi will be my feature function. Fit softmax with cross-validation, that's going to look at a lot of different values of the regularization strength C, and both penalty types L1 and L2. So that's a pretty big grid of hyperparameters. You have to fit a lot of models, especially with CV at 3 there. So that's going to have to fit a lot of models, and if you do it on the full data set, it will just take too long. So one approach you might take is to set those hyperparameters based on a small subset of the data. Here I've done it at 10%. You can see they get printed there. So this model chose C of 1 and penalty of L2. And then having made that selection, you could play it forward, right? So here now same feature function, but now it's fit softmax classifier with pre-selected parameters where I just hard code in the values that I selected from my earlier experiment. And then you go forward. And in that way, you got some of the benefits of exploring the hyperparameter space without all the costs. Make sense? Any questions or comments or concerns you want to bring out?
The random sampling method, is it just assuming there's subclasses of questions, like say entailment, contradiction, neutral, will it guarantee you an equal number of each, or the matching distributions based on the data sets, or is it truly random?
It's truly random, but because the data set is almost exactly balanced, you get balanced subsets out. But I think you're raising an interesting weakness of the approach I just sketched, which is that 10%, how do I know how representative is it of the true full data set? And in particular, the feature space that you form on that tiny subset might be very different from the one that you get from the full training set. And for example, that might deeply affect how much regularization you want to do. And I think that's a weakness of the current approach. That makes sense? So that's just to be, like, that's a compromise of that one. Here's another method that you might use that has not that weakness, but maybe others. And this would be hyperparameter selection with a few iterations. So all of these machine learning models, they go through a certain number of epochs of training. And a single epoch might be manageable, but if it takes 1,000 for your model to converge, that's where you're incurring the real costs. So another approach you might take would be to, as I've done here, fit softmax with cross-validation small iter, where I just find the parameter for the model I'm fitting there, it's max iter there for logistic regression, and set it to a very small value, like 3 or 5. And then I do the full grid search that I wanted to do before. It's just that that takes much less time, even if I do it over the whole data set as I'm doing down here, because the iteration number is so low. And again, you get a report down here. Here it shows L1 as the regularization parameter, not L2. And the performance is slightly better. And then you apply that forward in the way that I showed you before. So the implicit assumption you're making there is that the future for training epochs is going to be like the past, that a setting that was really bad early on is not going to somehow emerge as the hero of this story later. Once bad, always bad. And conversely, the ones that are good right out of the gate are probably the ones that will be good even if you run the model to convergence. I'm not offering you a guarantee because I think no such guarantee could be offered, but rather that this might be a good compromise given a budget that you have on training time or on compute resources and so forth. And you could mix and match these because both of these things, in the grand scheme of things, are very quick compared to fitting a model on the entire data set. One more thing here, and then we might wrap up. I just wanted to show you how easy it is in the framework to set up and run a hypothesis-only experiment. And I think this is pretty obvious. There's the feature function, hypothesis-only unigrams phi, takes in 2 trees, T1 and T2, but then it operates only on T2. It just throws away T1. I used fit softmax classifier with pre-selected params. I ran the experiment, and lo and behold, 65.3 for the macro F1, right? That is very different from a random baseline, which would be like 33, 34%. That shows you how powerful this can be. So if your model is at 68 and you feel like, oh, that's wonderful compared to random, well, you should contextualize it in this way. And I hope that's not dispiriting. And it's worth checking to see how much information is in the premise. Actually, I'm going to do that as a follow-up. Oh yeah, there it is compared to random. And actually here I just wanted to show you, just in case you didn't know this, that scikit has all these great dummy classifier models that allow you to fit models that just make use of the label distribution or just guess at random. And so here I just did the diligent thing of actually using one of those, and sure enough, yeah, 33.4%. So the hypothesis-only baseline is a very strong baseline. Questions about that?
Hypothesis-only baseline. Should we should we make the baseline the doing all the exact same operations as our model, but only on the second tree, or should it be just like the counter?
Oh, that's a great question. So what is given the model that you're developing, what is the true nature of the hypothesis-only baseline? That's a judgment call. Because, for example, if I picked word cross-product features as my basic feature function, that's undefined if I'm looking only at the hypothesis. And so I'd have to say, well, the unigrams are pretty close to being like my true feature function. But it's a tough thing to say, especially if you've defined a lot of features that make use of both the premise and the hypothesis. But if it's hand-built features, I might just default to unigrams. Seems pretty plausible. And then for the deep learning models, I think these questions are typically more straightforward. Good. I think rather than diving into those, let me leave this for next time. So next time we're going to look at sentence encoding models, where you get a separate representation for premise and hypothesis. And then we'll look at chain ones, which more or less just put the two together into a single, typically an RNN of some kind. And then we'll look at attention mechanisms and do some error analysis. And if we get through that, as usual, we'll leave some time for you to just code on homework 4 with the teaching team available for you. Great.